Dear students, good evening. Let us start. Let us continue our video lectures with division, right? So here, so in this case, first let us see the terminology. Okay. So in case of a division of binary numbers, we have a specific algorithm for doing accomplishing this. As per the textbook, we are going to learn this algorithm called restoration division or restoring division, right? So I'll explain why this method is called restoring division, right? So what we are going to learn is, first we are going to learn the traditional method, then we are going to learn how to convert this traditional method to this restoring division algorithm, right? So before that, let us get habituated with this traditional method. For that, let us discuss the terminology behind this division. So division, what we do dividend by divisor, right? So these are the inputs to the algorithm, and we are going to get the outputs as quotient and remainder. We are going to find quotient and remainder, right? So this is the thing. So dividend, always remember that these are 2n bits, this is n bit, right? So quotient is n bits and remainder is n bits. So what we are trying to do, we are trying to divide 2n bits by n bits, right? Right, for example, I can say that, I can give example that 10 bit by 5 bit division. So for this I am going to get a quotient as, so the output will be quotient as will be 5 bits and remainder will be 5 bits. First you note this. Okay. Now let us see in case of pen paper, using the traditional pen paper method, how we perform this division. Okay. So for that, let us take one example, like textbook example, right, as I follow from Morris Manor book. These are the examples given in the Morris Manor book, right? So let us follow the same example to define this thing. So we are trying to do this division of 448 divided by 17. If we do this, we will get 234 ja, right? You will get 6 ja, 102, 6. So you get 26 as quotient and 6 as the remainder. The same thing I am going to represent this 448 with 10 bits to do this binary division, right? So 17 with 5 bits, right? So finally I get a remainder as 5 bits and quotient as 5 bits. Okay. This is very important to note this, since if they give different example, you should able to map your algorithm this way. You can able to analyze your solve this problem this way, right? So please note that sometimes they'll give this bits also in the exam. So mostly they'll ask, okay, if they ask theoretically, you can take your own example. Okay. So 448 is represented is a dividend. It is represented in 10 bits like this, right? 0, 1110, 0, 0, 0, 0, 0. This is a quotient. Okay. And the sorry, this is a dividend, and the divisor is nothing but 17. 17 is nothing but 10001. Okay. Now what we need to look here first. Okay. So see what we need to look here. First we need to compare one this. Okay, let me write here. So 10001. So first let us compare this 0, 1110, 11110. So I want to compare 0, 1110 and 10001. So this is always, this is, you can by observation you can tell that this is less than this, right? So less than means what decision is taken? It does not go. Okay. So that's a scene, right? Less than means does not go. We need to decide that what we need to take decision. We need to decide the quotient bit. So if does not go, so since it is less than, does not go. So does not go means what is a thing? What is the decision we need to make? Quotient is nothing but 0. So quotient is 0. No need to do subtraction. If the quotient is 0, what is the thing? No need to do subtraction, right? So write as it is 0, 1, 1, 1, 0, 0 0 0 0 0. So what you are trying to do, you are comparing the first 5 bits of the dividend with the 5 bits of the divisor. So since the dividend is less than the divisor, it does not go. So we have taken decision that decision is, that's the quotient decision we need to take every time. So quotient decision is 0 here, right? Now we consider the 6 bits, right? So 0 1 1 0 0. So this 6 bits, and we write with this, right? So this is the second iteration, right? So we need to shift right one time the dividend and write. So then we compare this. Now we compare 0 1 1 0 0 with, so obviously this is a 6 bit, so this will be greater, right? Now if since 0 1 1 0 0, now if you take the magnitude of this, this will be definitely, it is greater than 1 0 0 1. So it goes. If you go, it means what, go means what's the meaning? Quotient bit will take quotient bit as 1. Then if quotient is taken as 1, then we need to subtract. We need to subtract, right? So how to do subtraction? So do 0 minus 1 0. So 1 we take borrow 2. So 2 minus 1 1. So it is left with 1. 1 minus 0 1. So we have taken borrow 0. 1 minus 0 1. 1 minus 1 0 0. Right? Now 0 0 1 0 0 1, right? 0 0 0 0. Now, right? So this is whatever we got here. So or here. So this one or this one. So these are called what? These are called, okay, these are called partial remainders. So every time we are going to get the partial remainders until we get the final remainder, right? Now what we need to do? Again I need to shift left, shift right and write this. So 1 0 0 1, right? And again I need to compare this 1 0 1 1 0 with this 1 0 1, right? Definitely it is bigger, right? By observation you can tell it is bigger. So you can write as 1 and again you can subtract. If you do subtraction, 2 minus 1 1, so here 1 you have taken borrow 0, 1 minus 0 1 0 0, okay, 0 0 0, right? Now again you can write this, right? So here this is again, this is what? This is again the partial remainder. This is again the partial remainder. So here what decision you take? You compare this 1 0 1 1 0, right? Since this is greater than 1 0 0 1, you have taken decision to be q equal to 1. This is what you did here, right? Now again you compare this 1 0 0 1. So you can see here. So this is, so here you can check here 0 1 0 1 0. This is the dividend is less than 1 0 0 1. So what you need to do? You need to take decision that quotient is 0. So quotient is 0 and you need to write as it is 0 0. No need to do subtraction in that case. 1 0 0, right? Now, okay, you need to again shift right and write 0 1, right? Now obviously you can check that 1 0 1 0 0 is greater than 1 0 0 1. Okay, now since it is greater, q equal to 1, right? Since q equal to 1, okay, now you can subtract. So subtract means 2 minus 1, 2 minus 1 1, right? 1, right? 0 0 0, okay, and you get a 0 here, okay. Now final thing, right? So again you can shift this 1 0 0 1, right? Since it does not go, so you can compare, right? 0 0 1 1 0 is less than 1 0 0 1. So quotient will be 0, right? Since quotient will be 0, you need to take decision, quotient will be 0 and you need to write as it is. What is this? 0 1 1 0. What is this? 0 1 1 0, right? This is nothing but 6, right? What about quotient? 0, 1, 1, 0, 1, 0. This is 2 power 1, 2 power 2, 2 power 3, 2 power 4. 16 plus 8 plus 2. This is nothing but 26, right? So this is what the traditional method, Babu, right? So every time what we are trying to do, we are trying to compare this dividend with the divisor. If the dividend is greater than the divisor, means it goes. So what we do, we take decision that quotient as 1 and we subtract the dividend from the quotient, right? Now if it does not go, what we took, we take quotient as 0, so we don't need to perform subtraction, directly we'll write this, right? So this is what the thing we implement using the pen paper method. But in case of hardware implementation, there is a little change. So one of the changes you can see there, instead of subtraction we can do 2's complement addition. That is one change we will do, right? Another change is another important change is, instead of, so every time what we are doing, we are to compare the thing, we are shift writing the we want to shift write this dividend and write, right? We want to shift write this divisor and write here, right? So instead of shift write the divisor, what we need to do, we shift left to the partial product, right? So we fix this divisor and we shift left to the partial product. So this partial product I told, sorry, not partial product, partial remainder. Okay, sorry, pardon. So what I am trying to tell is, so I am trying to explain what changes we are going to do, want to implement in the hardware. See, in that case, one of the important changes, instead of subtraction, we can perform the subtraction with 2's complement addition. That is one change I will do, right? So also the advantage is, if I do that change, if I do that subtraction with 2's complement addition, also I can compare the two numbers. So what is that? So now instead of this subtraction, I can do 2's complement addition, and based on the end carry. So if end carry equal to 1, I can tell that, right, dividend is greater than divisor, right? So if I, so what I am telling is, if I do dividend minus divisor, this thing I need to do. So in pen paper method, what I am doing, first I am doing subtraction and then I am comparing, right? So instead of that, so I am comparing. See, first I am comparing. Okay, let me tell here. Sorry, let me see here. What I am telling is, so suppose I want to compare 0 1 1 0 with 1 0 0 1, right? So in pen paper method, what I am trying to do, I am trying to compare by inspection, right? So by inspection I know that this is less than this one, so I took decision as quotient as 0. So in traditional hardware, how I do is, I don't know, right, by manually I cannot compare, hardware need to compare. So what I do is, first I perform the subtraction, right? So what I do, okay, let me show that here. First I do the subtraction, okay? First I do the subtraction. What subtraction I do? See here, what subtraction I do, I want to do this, I'll directly do. So I don't know whether this is less than this or greater than this, I want to tell that. So for that what I do, I'll do 0 1 1 0 minus 1 0 0 1. So instead of subtraction, I do the 2's complement, right? I take the 2's complement of this, right? 0 1 1 0, 2's complement of this. What is 2's complement? 1 1 1 1 0. Now I perform the addition. So 0 plus 1 1 1 plus 1 0 1 1 1 1 1 1. Now what is the meaning? Carry is 0. If carry is 0 means what is the meaning? So I get the end carry is 0. So I interpret that by looking at this end carry, I came to know that 0 1 1 0 is less than 1 0 0 1. So this is how I implement in the hardware. So directly I perform the subtraction first, right? So after performing the subtraction, then I interpret whether this number is less than this number or this number is less than this number. So suppose I perform the subtraction here, listen here, I perform the subtraction here. So what is the end result? I got end result as 11101 and end carry 0. By end carry 0, I came to know that this is less than this number. But whenever the dividend is less than this number, I should not perform subtraction, right? Understood? I should not perform subtraction, but I perform subtraction. So what is the partial remainder I should get? I should get 0110, right? This thing same as it is I should get, but I got this. So what I need to do? And again I want to get from this result, I want to get this result. I want to get this result 0110. So how to get back this? For that again I need to add this. Again I need to add this 10001, directly add this. So 1 plus 1 0, carry is 1, 1 1 1 0 1, ignore the carry 0 1 1 0. So that's, so here this step is called what? Restoring step. That's why restoring step, right? So in case of hardware implementation, what I am trying to do is, so in case of manual inspection, first I am comparing these two numbers manually and taking this decision. But in hardware what I do, I take this, I perform subtraction using the 2's complement method. Then based on the end carry, I will come to the conclusion that, so whether this number is greater than this number or less than, but if end carry is 0, we know, you know that this number is less than this number. So if this number is less than this number, I should not have done this subtraction, but I did that, right? So what I need to do, I need to get back my original partial remainder, this remainder 0110. To get back this original partial remainder 0110, what I need to do? I need to again add this. I need to add this to this result. So this adding of this 1001, this adding of this divisor to get back the original partial remainder, So that's why this is called a restoring. We are restoring this partial remainder. That is the meaning. We are restoring this partial. This is this case. For example, take another case. This is one case you can see. In this case, we need to restore. So suppose if carry is 1, we no need to restore. So for example, you take this example, right? For example, you take this step, right? You take another example, okay? For example, you take the second example. In second example, what we are trying to do? We are trying to do this 11100 and 10001. So I want to know whether this is less than this or greater than this. For that what I do? I do this subtraction. How I do this subtraction? 11100, I take the 2's complement of it, 10 1110, right? And I perform the addition, right? I perform the addition. So sorry, this is 1 right? This is 1, right? 2's complement of this is 1, then 1110, right? So then perform the addition. So 1 1 0 1 1 1, right? 0 1. So end carry, what is end carry? So end carry is 1, means what is the meaning? So end carry is 1 means I can say that 11100, that is dividend, is greater than 10001, that is divisor, right? In this case, what is the meaning? Quotient is 1, right? In this case, quotient is 1, right? And also I need to do subtraction. I already did the subtraction, so no need to restore, right? So in this case, I need to do subtraction. You can see here the partial remainder will be 0 1, right? 0 1 1. This one, this is the partial remainder, right? This is a partial remainder 0 1 0 1 1, as it is I got this partial remainder. So in this case, no need to restore, right? The same trick, if you understand this trick we are going to apply on our hardware algorithm, okay? So let us, without wasting time, let us go back to the hardware. So this is the hardware, okay? So in this hardware, okay, so what we are trying to do in this hardware, we are going to first divisor. So in our case, the divisor, whatever the divisor, so you see that, so this is the divisor 10001, right? So this divisor 10001 is initialized in the B register, okay? So this is the hardware, so which we use 10001 we initialize in the B register. Similarly, so what we are trying to do, we are trying to do 2n bits by n bits, right, n bits. This 2n bits, this n bits bottom denominator we are initializing the B register. This 2n bits we are initializing in the A register, right. So this 2n bits, what is this 2n bits? The numerator, what is the numerator? 0, so 1 1 1 0, this is the upper 5 bits, and the lower 5 bits 0 0 0 0 0. So this we are initializing in the AQ register, right. So this we are initializing in the AQ register, okay. Similarly, sequence counter, so what I am telling is I want to do 2n by n bits. So in the hardware, what we do, we initialize the AQ with this numerator 2n bits with the AQ. This is the 5 bits, for example in our case A, this is the 5 bits, right. So the higher 5 bits we initialize in the A and the lower 5 bits we initialize in the Q. Similarly, the denominator 5 bits we initialize in the B, right. This is initialization, right. So similarly, we have the sequence counter for doing the count operation, right. So how many times we need to count, right, how many times we need to count, how many times we need to repeat these iterations, right. So in this case we are repeating 5 times, so this iterations, so what is the iteration? Every iteration I need to do shift left, right, and perform the subtraction using the 2's complement addition, right, and then based on the end carry, this is the end carry, we store this end carry, based on this end carry we need to take decision. What decision? So this is the quotient bit, so we need to take the decision here, always we take the decision and keep the result in the Qn bit, right. In the Qn bit we put that decision result, so we need to decide, right, whether the quotient is 1 or 0 in every iteration. So that decision we will take based on this E bit, end carry bit, and we put the quotient in Qn, right, 1 or 0, okay. So let us see what I am trying to explain. Let us visualize this with the example, right. Let us visualize this with the example, right, this algorithm in the hardware. Now I have this initialization in the hardware, right. Let me try to show the same thing whatever I did here with this values I did with the hardware now, right. Now let us see that, right. So without wasting time, let us see that. So what I am telling is the denominator divisor, right, this is a divisor, this is the divisor. So this divisor B I am 0 0 1, right. So I also want to do this B complement plus 1, that is a 2's complement, right, 2's complement is 1 1 1 1 0, right. Now E the carry is 0, AQ is initialized with the 2n bits, right. So what is that numerator? 0 1 1 1 0, right, 0 0 0 0 0, and the sequence counter is initialized with the 5, right. So 5 times we need to repeat this process. So every time what I told, this is the thing, let me tell the first iteration. So every time what I do, I need to shift left, right, shift left what? EAQ, I need to shift left, right. So shift left, so 0 will come here, right. So this 1 1 1 0, right. So this 0 will come here, so on, right, 0 0 0 0, here you keep as empty, right. So here you keep as empty, why means here I need to take decision in this step, right. What the decision, whether for this iteration the quotient is 0 or not, so that decision I need to take and keep that result here, I am storing that result here every time, right. Now what I need to do, I need to compare this and this, right, A and 1 0 0 1. So for that comparison what I need to do, I need to subtract this with this. So instead of subtracting I do this addition of 2's complement, right. So this is what you do, A plus B bar plus 1, the result is stored in EA, right. So do this 0 1 1 1 1, you do this, so 1 1 0 1 1 1 0 1. Now what is the meaning? So E equal to 1, So E means what? E equal to 1 means what is the meaning? A is greater than or equal to B, right. So this numerator is greater than denominator. So in that case what is the decision I told? So Qn will be 1. So in that case Qn will be 1. So 0 0 0 0 Qn will be, so here the decision I am taking every time. So in this case since end carry is 1, that means A greater than or equal to B. So quotient bit I am taking decision as 1, this bit I am taking decision as 1, right. Also now the sequence counter is decremented. So one iteration is over, it is decremented, this is over. Now again in the second iteration, so second iteration again starts with the shift left operation, shift left of EAQ. So shift left, so this 1 will go, so this 0 will come here, 0 1 0 1 1, this 0 will come here, 0, okay, 0 0 0, this 1 will come here, and there is again empty, right. So now what I need to do again, I need to do this operation, right. So 0 1 1 1 1, just addition, right. So 0 plus 1 1, 1 plus 1 0, 1 1 1 0 1 0, again carry 1, right. So again end carry is 1 here. So here I am doing EA A plus B bar plus 1, this is arrow, right. Now since E equal to 1, again A greater than or equal to B, since A greater than or equal to B, again Qn equal to 1, right. So here I will take decision as Qn equal to 1, right. So I reduce the iteration to 3, okay. Okay, this is the second iteration, right. Similarly third iteration, okay, let me write the previous result here. So previous result is E value is 1, so this becomes 0 0 1 0 1, this is 0 0 0 1 1, right. Now the right, so in the third iteration, so in the third iteration again, right, so this became 3 here, right, sequence counter became 3 here. In the third iteration again shift left of EAQ, right, if shift left EAQ 0, right, 0 1, right, 0 1 0 1 0, right, 0 0 1 1 dash, right. Again you need to do this 0, right, A plus B bar plus 1, the result is stored in EA, right. So 0 1 1 1 1, now 1 0 1 0 1 1 1 1 0. Now you see here what is the case, E equal to 0, E equal to 0 means what is the meaning, A less than B, A less than B means what, Qn is 0, so I need to take decision Qn is 0. But if Qn is 0, what I told, we should not do this subtraction, right, but we did this subtraction, right, to get back to restore, right. So in this case I need to apply the restore. What is the restore step? This is not the actual partial product, I do not want to do this, this is the actual partial product, right, 0 1 0 1 0 0 0 1 1 0, this is the partial product. To get back this original one, what I need to do, I need to add, what I need to add, I need to add this B, right, I need to add B, A plus B, so right, okay, I need to add this, so 1 triple 0 1, this I need to add, so 0 1 0 1 0 1, so this I got back my original partial product. So see this, right, 0 1 0 1 0, right, 0 0 1 1 0. So this step is called restoration step, right. So restoration step, that is why this division is called restoration division. If the quotient is 0, I need to do always restoration first, right, then this become 2, understood. Then in the fourth iteration, again what, shift left of EAQ, if I do shift left 0 1 0 1 0 0 0 1 1 0 dash, so again add this 0 1 1 1 1, right, 1 1 0 1 1 0 1 0, right, 0 0 0 1 1 0 dash. So again e equal to 0, right? So again e equal to 0 here, right? So 1 minute 0 1 0 1 0 0 0 1 0 0, right? 1 0 1 double 0 0 1 1 0 dash. Okay, 1 1 0 1. Oh sorry, here there is some mistake I did. Okay, let me do this addition one more time. See if you do little mistake. Okay, do the addition, right? So what is the result of addition? Here 1 1 0 1. So 1 plus 1 is 0 1 0 1. So sorry, here I get a e as 1, right? So I get a e as 1. So again e as 1 means what? A is greater than b, right? So I need to take decision as 0 1 1 0, quotient as 1, right? So that's it. That also this is decremented. So in the fifth iteration, so again you perform shift left. So 0 0 0 1 1 0 1 1 0 1 dash, right? Again you need to do this 0 1 1 1 1, right? So 1 0 1 plus 1 0 1 1 plus 1 1 1 1 plus 1 0 1 1 0 1 1 0 1 dash. So here again e equal to 0. So e equal to 0 means what? A is less than b. So here again I need to restore, right? So how to restore? Just add this 1 triple 0 1, right? So 0 1 1 1, right? 0 0 1. So 1 1 0 1. Here I need to take decision as 0, right? 0 0. So finally this is this 5 bits represents the remainder. This 5 bits represents the quotient. So finally quotient is there in the queue. Remainder, since 1 became 0 here, count became 0. So I accomplished all the rounds, right? You can check here 0, this is nothing but 6, this is nothing but whatever the, right, 26, you can check here, this is 26, this is 6, right? So this is the method. I hope you understand this. In the next I'll make one more video to explain the algorithm. Thank you.